All right, so then for number 9, we are finding the derivative for each of these. So for number 9, we have two things being multiplied. That means we're going to need to use product rule. So we're going to do first times derivative of second plus second times derivative of first. So we just copied our normal first. Derivative of x squared would be 2x plus we just copied our normal x squared. And now we want to take the derivative of this guy for the derivative of our first. All right, so the derivative of anything to the 5th power is going to be 5 that thing to the 4th. Then we're going to multiply by the derivative of that thing. So the derivative of x cubed would be 3x squared plus 5. So this is derivative of the outside. This is derivative of the inside. All right, so first times derivative of second plus second times derivative of first. Now we're going to simplify, and there are a couple of ways we could do that. So I pulled this 2x out in front, and then here's our x cubed plus 5x to the 5th. Over here, I don't have to multiply this to the 4th power, but I can distribute the 5x squared to this 3x squared plus 5. So if I take 5x squared times 3x squared, that's 15x to the 4th. And then if I take 5x squared times 5, then that's going to give me 25x squared. And then we still have our x cubed plus 5x to the 4th. All right, so that would be one way we could leave our answer. Another thing we could do would be to take out our greatest common factor. So I have one term right here, and I have a second term right here before I simplified it, right? And so you can see that in this first term right here, I could take out an x, and in this second term, I could take out an x. I also have 5 of these cubics here, and I have 4 of them here, so I could take out 4 of them. All right, so again, we took out an x, and we took out 4 of the cubics. So if I do that, then in this first guy right here, what's going to be left is this 2 and 1 of the cubics, so 2 and 1 of the cubics. Then over here, if I took out an x, I'm going to have this x left, and then I'm going to have this 5 left, and I'm going to have the 3x squared plus 5. All the cubics are gone, right, because I took all 4 of them out. So I would just be left with the 5x times 3x squared plus 5. All right, so if I go through and I put that together, that's going to give me 15x cubed plus 25x squared. So now if I simplify, I'm going to distribute my 2 right here. So 2x cubed plus 10x plus 15x cubed plus 25x squared. And so I can put my 2x cubed and my 15x cubed together and move descending power order. I'm going to put the 25x squared next, and then the 10x. So for number 10, they gave us secant squared x cubed. You might prefer to write it this way, the secant x cubed, that whole thing squared. So if you have anything to the second power, the derivative of that is going to be 2 that thing to the first power, so that's the derivative of the outside. Now I need to do the derivative of the inside. All right, so the derivative of secant anything is going to be secant that thing tangent that thing, and then times the derivative of that thing. So if this had just been a plain x right here, the derivative of secant x is secant x tangent x. But because it's secant of a quantity, the derivative of secant anything is secant that thing tangent that thing, and then we have to take the derivative of that thing. We have to take the derivative of that quantity. So the derivative of x cubed would be 3x squared. So about the only simplification I could do, put the 3x squared together with this 2 out here. That would be 6x squared. And then here I have a secant x cubed to the first, and here I have a secant x cubed to the first. So if I multiply those, that would just give me secant x cubed to the second. And then I still have my tangent x cubed as well. All right, then for number 11, again, continuing with taking the derivative, we've got the cotangent of the sine of x. Now, this is not cotangent times sine x. There would have to be an x here for that. This is the cotangent of the sine of x. This is what we're taking the cotangent of. All right, so the derivative of cotangent anything is negative cosecant squared of that thing. and then we're going to take the derivative of that thing. So the derivative of sine is cosine. All right, for number 12, this is sine of x to the fourth. That doesn't mean that I have 4 sine x's, right? Like if I had sine x to the fourth, that whole thing to the fourth, then the 4 would be right here. This is the sine of just x to the fourth. Sine isn't being raised to the fourth, only the x. So you can't like take the square root of this and get sine x squared is our point. So instead, I'm going to rewrite this. So remember that anything to the square root of anything is going to be that to the 1/2. Numerator is my exponent, denominator is my index. Again, you can't say like 4 times 1/2, like a power raised to a power, because this whole thing is not being raised to the fourth. It's only the x being raised to the fourth. All right, so I'm going to take the derivative of the outside. So anything to the 1/2 would be 1/2 that thing to the negative 1/2. And then I'm going to take the derivative of the inside. All right, so if I take the derivative of the sine of anything, it would be cosine of that thing times derivative of that thing. So one more time, if I have sine x to the fourth, the derivative of sine anything is cosine that thing times the derivative of that thing. So the derivative of x to the fourth would be 4x to the third. So a couple of different ways that we could write this. We could combine the 1/2 with the 4 and have 2x cubed, and we could leave everything written with exponents, like with this negative 1/2. If instead they want me to write it with radicals, all right, so again, I've still got 4 times 1/2, there's my 2x to the third, and I've still got this cosine x to the fourth here. If I'm going to rewrite this guy as a radical, the negative makes it move down to the denominator. And then remember, the numerator is my exponent, the denominator is my index. So this is sine x to the fourth, that whole thing to the first power, and then the square root of that. If they didn't want me to leave a radical in my denominator and I had to rationalize it, then I could multiply top and bottom by the square root of sine x to the fourth. So if I did that, you can see I end up with a square root of sine x to the fourth in the top, and then down here in the bottom, that radical is gone. So again, you can leave it written with fractions as exponents. You can rewrite it as radicals, and if they make us rationalize it, we could do that as well. All right, then look at number 13. So for number 13, we've got 1 over the inverse cosine of x. So I could do quotient rule here, denominator times derivative of numerator minus numerator times derivative of denominator, but I'm always looking for a way that I can rewrite this so I don't have to use a product or a quotient if I can. So for this guy, I could rewrite this with a negative exponent to get it out of the denominator, and then I can use power rule and chain rule, right? Now, for these inverse trig functions, I told you I would give you the derivative formulas only for the inverse trig function. So here is that derivative of the inverse trig function I'm going to need. So anything to the negative 1 is going to be negative 1, that thing to the negative 2. So there's the derivative of the outside. Now I need the derivative of the inside. So the derivative of inverse cosine is just this formula over here, right? So I can just put that derivative there. So again, anything to the negative 1 would be negative 1, that thing to the negative 2, times the derivative of that thing. And derivative of inverse cosine, this is the formula they gave us. All right, so to simplify that a little bit, negative 1 times negative 1 is going to be positive 1. So again, I could write this with rational exponents. So if I did that, this guy, I've already got my inverse cosine x to the negative 2. For this guy, if I'm going to get it out of the denominator, it would need a negative exponent. And remember, square root is raising it to the 1/2. So numerator is my exponent, denominator is my index. So that's how I could write it with rational exponents. If instead I wanted to write it as a radical, then we could say negative 1 times negative 1 is positive 1. And then inverse cosine to the negative 2, to get rid of that negative exponent, we move it to the denominator. And then we've still got our radical down there. If they required us to rationalize it, I would just multiply top and bottom by the square root of 1 minus x squared. So then here's the square root of 1 minus x squared in the top, and we've gotten rid of that radical in the bottom. So because the quizzes are multiple choice, you need to understand that, maybe you get this as your answer, but it could be written this way, or it could be written this way, or it could be written this way, and you would need to be able to recognize any of those forms of that correct answer in the multiple choice.